When we start to apply equilibrium to items that are not solids but rather are fluids, then we have to keep mindful of a couple of things. And in this kind of course, what we're really doing is trying to ask the question, what are the effect of the fluids on a solid object, a rigid body type object? But there's different ways that we can kind of look at this. And so typically in this kind of scenario, we're looking at what the forces are and the reactions that are developed on the solid object, that in this case being this gate type of thing. And so when we draw the free body diagram of it, we want to take advantage of things such as BC as a two-force member because it's pin connected on each end. It doesn't have any loads applied, and so that immediately tells us the orientation of the unknown force there, BC, and in this case being at 60 degrees from the horizontal, right? And then we got this pin support down here at the end, at the bottom. So we've got then an A Y and an A X. Right? That's great for potential reactions, but how do we want to handle the actual fluid force? And although you could do this in two different ways, strip off all the water, it's usually easier to keep yourself in a nice Cartesian coordinate system in terms of the results. So why not take a vertical plane, and then that means that we have this whole volume of water that's sitting there. Right? So in effect, we've just cut through this plane here, retained that water, and we have a weight vector then at the center of mass of that water wedge. And that's nice because then, and that's easy to get, right? Because that weight is going to be equal to the unit weight of the material, 62.4 pounds per cubic foot in this case, times then that volume, which will be just the volume of that little triangular piece that's there, typically done per foot in depth of the page. And then remember that our pressure variation at any point, P, right, and really that's pressure, so all the rest of the water pressing in on that point, pressure is equal to gamma times our depth wherever we're at, how far we're deep. So it varies linearly from 0 at the free surface to then a maximum at the bottom, so the total height, and it's going to be pushing sideways. So we'll call this whole height h. And so down here at the bottom, then we've got a max pressure of gamma times h, and so that'll be then pushing sideways. It's always perpendicular to the surface that we've made that cut, always normal to that cut, and that resultant then that we get is then just the volume of that pressure prism, and in this case located at the centroid, 1/3 of the height. So there's your hydraulic force resultant. So R will equal the height, which is gamma h, the base is gamma h times the height, which is h. So a gamma h squared, and then it's a triangle, so divided by 2, and it's located again at that centroid, which will be h over 3. And then from there, you can then do sum of moments, say about point A to get your BC force, or you can do sum of moments about point B in order to get ratio between AX and AY. Right, so that's not so convenient, right, because you kind of want both of those. So you can go up and extend the line BC to where then AY and BC would intersect with each other, and you can then some moments there to find AX. And cleverly, you could also come down here where BC and AX intersect, and you could end up then finding out what the magnitude of AY is by the sum of moments equation.